is that when we're looking at Newton's first law here, excuse me, Newton's third law, it's the law that tells us how objects interact with each other. So let's think about this thing here. So what I want to do here is that I want to apply a force on a water bottle and push it with my hand. So I'm going to apply a force on a water bottle and push on it. So picture-wise, I imagine that I have something like this. And then I have my water bottle. So I'm thinking about some type of water container. And of course, it's got to be filled with water. And what I'm going to do here is that I'm going to come in with my hand. And I'm going to come in and I'm going to apply a force on this water bottle right here. Right? That's my pushing force. So here's what we know. What we have here is that we have two interacting objects, right? There's my hand, and then of course, there's the bottle. And here's things that we can conclude about this. The first thing that I would say here is that any contact between two objects right, requires a single interaction between these two. That means me coming in contact with the bottle is, of course, only a single interaction. It's not like I touch the bottle and then the bottle touches me. It's all simultaneously. So then this means that this in turn requires not one, but two forces. And these forces, when we talk about these forces are typically called the action and reaction forces. So Newton's third law really sets this up right here. And so here it is. And this is known as the action-reaction law. That's another way that people state it here. But it's fairly simple here. It says that whenever one object exerts a force on a second, the second object exerts an equal and opposite force. And I think this law is really counterintuitive, like really, really counterintuitive. And I'm pretty sure that most of you may have already heard of this and sort of like, yeah, if I was to give it to you on an exam, you'd go, yeah, this is the answer. But the question is, can you internalize this thing? Okay, so picture-wise, let me set up two pictures. I could imagine that I have two blocks. And these two blocks are coming towards each other. Okay, that means they're sliding towards each other right here. And what are they going to do? They're going to interact. And then a moment later, they actually collide here. So when I look at this collision, it's looking like this here. Right, so I have this scenario here. So I got 1 and I have 2. They're now interacting. What Newton's laws say is that the force of 1 acting on 2 is then going to be equal and opposite to the force of 2 on 1. In other words, we're really saying that the force of 1 and 2 is equal and opposite in magnitude to 2 and 1. In other words, the strength of these forces are exactly the same. And like I said before, you may have already seen this. You're probably going like, well, yeah, of course, this is what's the way it behaves. Yeah, I give this to you on the exam. Yep, you're going to be all good. You'll figure it out. No problem at all. My job here is not to necessarily, get you to regurgitate material. Anybody can do that. But to internalize it, right? To internalize this thing. And the way I'm going to try to look at this is that I'm going to look at some examples here. Let's think of some fairly simple examples. You could imagine pushing on a wall. And what I mean by pushing on the wall here, you could imagine that if you have a scenario here where I have a wall, maybe it's a brick wall, and you got, certain number of red bricks here, and then you have some guy or girl that's doing what? They're pushing on the wall. So according to Newton's third law, it says that if I apply a force in this direction, right? This is the force of, of the push. Newton's third law says that there has to be an equal and opposite force of the wall pushing back. Right? And a lot of times people say, well, wait a minute, the wall's not moving. So of course we could have done this before here. We could have done this and go like, but wait a minute, why couldn't I have said this with Newton's second law? Why couldn't I have said, well, wait a minute, well, the wall of course isn't moving. Its acceleration is 0. Its net force is 0. So of course, the magnitudes of the wall and of the push are exactly the same because you have balanced forces, right? That makes sense here. But wait a minute. What if the wall is pushed down? What if this person was so strong that when you look at the pushing now, right? What you have now is that the wall now is being knocked down. That means that when you go and you look at these bricks here, this whole thing is starting to come down now. Why? Because this person is pushing so hard. He's pushing down the wall, right? He's pushing down the wall. So what's a common statement? The common statement is that, right? A common statement is this person is pushing harder than the wall, right? He pushed down the wall. Of course he's pushing down harder. Wrong. Newton's third law says that the force of the wall is equal to the force of the push. That's what Newton's law says. For every action, there's a reaction, right? So in this case, let's say he was the action, it's arbitrary, then the wall is the reaction. So right away, you might be saying, but wait a minute, that can't be right. Because of course he pushed harder than the wall. Otherwise, the wall would be standing. Wrong. Newton's third law says they're exactly the same, right? And we can also think about an example of just plain walking on the ground, right? If you're thinking about walking on the ground, and I think about Newton's third law, here we go. So you could imagine that here's my surface now. And then there's a person walking. What does that person have to do in order to move forward, right? In order to move forward, he has to do or she has to push backwards, right? You have to push backwards to go forwards. So that means the force of the foot, in this case, I'll call it the action, then causes a reaction where the force of the ground is then the reaction. And this means here that how hard you push on the ground determines how hard the ground pushes you in the forward direction. So you need N3L to explain walking. And if you've ever had a very slippery floor and you have socks on, note that you can't walk on the floor very well. And that's because when you try to walk on it, you can't push off very hard backwards, so the ground can't push you forward by very much. Newton's third law says that the force of the foot must be equal to the force of the ground. Note that I was careful not to say friction. Because what you're seeing here is that there's actually two forces that are actually being applied by the ground. It turns out that if this is the ground, you cannot apply a horizontal force only. So when you actually have your force of your foot, you're actually at an angle. So now, when you look at this, you need some components. There's the force of friction, and then a piece of this has to be the normal force. So there's two forces that are being applied on you to the ground, one to support your weight and the other one to, move you in the forward direction. So it's not so simple. That's why I said the ground and not the normal force or not friction. So that's the same thing happens with the car, right? If you're thinking about, what makes a car go forward, if you look at the wheel, and this is the ground, the wheel is what? Well, it's rotating in this direction. So then the wheel then applies a force where? On the road in this direction. So this is the force of the tire. So the reaction, of course, has to be the force of the ground, pushing it forward. So there's more to it there. I mean, there's a lot of other little silly examples that we can look at. I don't want to say them silly, but that makes sense here, right? Sort of like, why does a fish swim forward? Right? Here's another example. Well, so you could imagine you have a fish. And of course, the fish is in water. And what you're seeing here is that in order for a fish to move forward, he has to take, or she has to take her little fin and do what? Apply a force backwards. So the force of the fin is pushing on the water. So what actually makes the fish go forward? Not the fin. It's the push of the water off the fish, right? So here's my reaction, and over here is my action. So these forces always have to be the same, right? Newton's third law is very clear. It says that the force of the fin has to be the same as the force of the water. We're only talking magnitudes, of course. Right? So in summary, we could say here that there's always an action and reaction pair with any interaction, and forces are always equal in strength, where one of them has to be in opposite direction. And that kind of makes sense here, right? That's what we do here. However, does it really make sense? Two of my favorite examples with Newton's third law here are as follows. Suppose you take Iron Mike Tyson versus this Carlos in a boxing ring. Man, that sounds like a really ugly interaction, right? That sounds like a really ugly interaction. So what happens? Eventually, Tyson knocks out Carlos. So when I say eventually, we're talking a very short time, right? He is done. He's out. Question. Who experienced the larger force? Right? Tyson's fist on Carlos's face, or Carlos's face on Tyson's fist. Well, I don't know what just happened. Right? Right? I know what you're supposed to say. Right? You want the points. So you're going to say, of course. Right? They're supposed to be equal. Okay, Michelle, I'm looking at giving you extra credit for that remark here. So, yeah, of course, they're supposed to be equal. Do you really believe it, though? Right? Right? Remember what I said. I want you to internalize this thing. Now, right? Newton's third law say they're exactly the same. Here's another extreme example. You're driving at night. right? Let's say you're on Highway 152, where you got all those fields. You're driving your big truck, right? You're really booking it down here. And you're driving at 90 miles an hour, right? You're really going here. And then out in the middle of the highway is this little tiny moth, right? You got this tiny, tiny moth. And then these guys collide, right? Who experiences the larger force? Sure, you might say, oh yeah, they're supposed to be equal. Really? You really believe that the force of this truck going 90 miles an hour is the same as the force of the moth on the truck? I don't know if I believe it, but I do and have internalized it because I have seen experiment after experiment after experiment. And in my bones, I know that they're the same. But if you're having trouble with this language, it's because you've been misled by everyday language, right? If you are having trouble with this, it's because you've been misled by the language, right? Even if this sounds crazy, the language is the problem, right? The language, it's the problem. And what you're finding here is that it's not about force. It's about acceleration. So when you're looking at two interacting objects, it's not the force that causes the damage, it's the acceleration. And so what you're seeing here is that you do have the force of the truck, right? We could say this is the force of the truck on moth. And Newton's third law says that the force of the moth on truck, they're identical. But the big difference is not about the force, it's about the mass. The truck having such a large mass means that the truck has a tiny, right? A tiny, tiny deceleration that the truck driver doesn't feel anything. Didn't even realize that he slowed down. But if you look at the mass of the moth being so tiny, this moth realizes for a very split second that it's in trouble because its deceleration is so high that it didn't, it really damaged it quite a bit. So this is a huge acceleration. So the best indicator is really about momentum and energy. But the best indicator right now of damage to an object is not force, but acceleration. Because you have a higher acceleration, we say you feel more. Because you have a lower acceleration, you feel less. So that's what we mean by Newton's third law right there.